Hi friends, welcome to our YouTube channel Nagaraju Academy. The main aim of this lecture is discuss about the TS Genco-2015 Solutions of 2015 question paper of electrical engineering in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever you upload a new video, the direct notification comes on mobile. If any improvements in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why to waste more time? So let's get started. So now we are going to solve the 11th question. See the question here. A moving coil of a meter has 100 turns and a length and depth of 10 millimeter and 20 millimeter respectively. It is positioned in a uniform radial flux density of 200 millitesla. The coil carrier current capacity is 50 milliampere. The torque on the coil is. So this is nothing but a moving coil PMMC, and these are the number of turns, and also they are given the area based on the depth and also the length, and then they also given the maximum flux density, that is a uniform, it is a constant one, and also they are given a current capacity. So based on these parameters, we have to find what is the torque which is going to produced on this coil. We need to figure out. So what are the four options? Option A, 200 micro Newton meter is the correct solution of this question. So let's discuss this one. So this is a PMMC meter, which is a permanent magnetic moving coil. So here this PMMC is always going to measure based on the average value. So therefore here in this question they are given the number of turns is 100 turns, and the length and breadth of the coil we are going to use here, which is 10 millimeter. So we are going to convert in terms of meter, which is 10 into 10 to the power of minus 3 meter, and also the depth of this coil is 20 millimeter. So in terms of meter, it is 20 into 10 to the power of minus 3 meter. So now in the question they also given the magnetic flux density, which is 200 millitesla. It is a uniform, means constant value. So 200 into 10 to the power of minus 3 Tesla. So in the also the current in the coil, which is 50 milliampere. So if you want to convert in terms of ampere, which is 50 into 10 to the power of minus 3 ampere. So based on this data, we need to find what is the torque which is going to produce on this coil. So the basic formula between this relation is, in the PMMC, torque is equal to number of turns into flux density into current into area of the coil. So therefore area is equal to L into B. So we have to do these two things multiplication, then only we are going to get the area. So we know each and every value, just substitute them and do the multiplication. So finally we are going to get 200 into 10 to the power of minus 6. It is not Newton per meter, it is a Newton meter. So therefore here this is 10 to the power of minus 6 is micro. So therefore 200 micro Newton meter is a correct solution of this question. So now we are going to solve the 12th question. See the question here. In an experiment with a thermocouple with one junction at 0 degrees centigrade, the following data were obtained at 0 degrees centigrade. It means, so thermocouple basically means there are two different materials are going to connect, so therefore at two different temperatures. So because of the temperature difference, there will be EMF induced in the thermocouple, and also the current is going to flow. So based on this, the EMS of each and every individual temperature also they have given in the diagram. So assuming parabolic relation, the calculated neutral temperature for this thermocouple will be about. It means that, so the diagram, the relation between the EMF and the temperature is a parabolic relation. So based on this, we need to find what is the neutral temperature. So neutral temperature means at what temperature we are going to get the maximum EMF which is going to induced in this thermocouple, we need to figure out. So neutral temperature is the temperature at which the maximum EMF in this thermocouple, the value which is going to induce, that we need to figure out at that particular temperature. So out of the four options, option B, 333 degrees centigrade. So 333 degrees centigrade. So at this temperature we are going to get the maximum EMF. So let's solve this numerical. So basically, what is the true meaning of a thermocouple? Thermocouple is nothing but here, suppose this is a material 1. Suppose this, let me assume this is a iron. So material 1, and there is another material which is material 2. Let me assume this is a Constantine. So based on Constantine, so these are the two different materials. So when we are using two different materials, and also at one is at a temperature of T1. Let me assume this is a temperature T1, and this is at a temperature of T2. So here let me assume this is at a cold temperature and this is at a high temperature. So because of the temperature difference, so because of this temperature difference, and also because of two different materials or metals are conducted, so because of these two reasons, what is going to happen, there will be a flow of current from higher temperature to lower temperature. So there will be a current flowing in the thermocouple. This is the basic principle of the thermocouple. So suppose if you want to measure the voltage, then what we are going to do is, here we are going to cut this iron or anything constant, and then we are going to place a voltmeter. So if you do this one, this voltmeter is going to deflect. So because of this temperature difference, and also because of two different materials we are going to join them, then there will be a point deflection is going to produce based on this temperature difference, and the relation is almost nearly equal to parabolic relation. So therefore the EMF which is going to induced here in the thermocouple, it is going to have a parabolic relation with respect to the temperature, which is A into T plus BT square, where A and B are called the constants of this thermocouple. So therefore here this is the true meaning or working principle of the basic diagram of the thermocouple. So this T is nothing but it is a temperature difference between the T2 minus T1. So in this question here, T1 is equal to 0 degree centigrade. So this is the 0 degree centigrade, and let me assume T2 is equal to T. So therefore the temperature difference will be T minus 0, which is T. So I have used here T. So now I am going to rub this one. So in this question they are given that one junction is at 0 degree and the other junction is at a temperature, varying temperature. So at 20 degree centigrade, the EMF is going to induce this 0.194 millivolt, and 100 degree centigrade we are going to get a 0.850 millivolt, and at 300 degree centigrade we are going to get a 1.650 millivolt. So based on this data we have to find what is the neutral temperature. So I am going to draw a plot diagram with respect to EMF and the temperature. Temperature is in the degree centigrade and the EMF in the millivolt. At 20 volt I have drawn the, at 20 degree centigrade I am going to get 0.194 millivolt, and at 100 degree centigrade I am going to get a 0.850 millivolt, and at 300 degree centigrade I am going to get a EMF induced of 1.650. So at neutral temperature means at what temperature I am going to get a maximum EMF, I need to figure out. This Tn is called as a neutral temperature. So this is what we need to figure out. So here we need only two constants. Only two constants are needed. So based on this here, there are, I am going to take here at 20 degree centigrade the EMF induced is 0.194 millivolt. So I am going to take this data and substituting this equation. So EMF is equal to 0.194 into 10 to the power of minus 3 volt is equal to, in place of temperature, 20 degree centigrade. At 20 degree centigrade I am going to get this much amount of voltage. So let me assume this is a equation 1. So for equation 2 I am going to take this second term. So therefore at 100 degree centigrade the EMF induced is 0.850 millivolt. So substitute these values here. So therefore 0.85 10 to the power of minus 3 volt is at temperature 100 degree. So this is the second equation. So only we have two equations with only two unknowns. The two unknowns are A and B. So two equations with two unknowns. So after solving this one we are going to get the unknowns as A is equal to 10 to the power of minus 5 and B is equal to minus 1.5 into 10 to the power of minus 8. So suppose if they ask what is the unit of the A, so unit of the A is nothing but voltage, volt per degree centigrade, and also what is the unit of the B, unit of the B constant, which is here voltage by degree centigrade square. So this is the units of the constants A and B. So now I want to know at this neutral temperature the maximum EMF is going to induced. So this is a parabolic, so therefore we can say this is going to have a, at this point the differentiation of the EMF has to be 0. So therefore whenever the differentiation of the EMF is equal to 0, then we are going to get a maximum EMF at that particular temperature. So therefore here we are going to do the differentiation with respect to temperature. So this equation I am going to differentiate. So A is nothing but A, it is going to give, so BD square we are going to get 2BT. So 2BT, T is nothing but at total temperature I am going to do the differentiation. So Tn is equal to 0. So if you solve this one we are going to get Tn is equal to minus A by 2B. So we have derivated the EMF equation and then we got a relation between the temperature and the constants. So neutral temperature is equal to minus A by 2B. So we know the value of A and we know the value of B. So substitute them and solve them. Finally we are going to get Tn is equal to 33.33. So 333.33. So it is nearly equal to 333 volt at degree centigrade. So at this much amount of degree centigrade we are going to get a voltage, maximum voltage we are going to get, and this is the standard relation with respect to temperature and the EMF in a thermocouple. It is going to always follow a parabolic relation, which is E is equal to AT plus BT square. So if you know this relation, then it is very easy to solve this numerical, and temperature Tn is equal to 333 degrees centigrade is the correct solution of this question. So now we are going to solve 13th question. See the question here. The measurement of a non-electrical quantity involves the following four subsystems. The one is amplifier block, and the second is display block, and the third is instrumentation block, and the fourth is transducer block. So based on this, the correct sequence in which these blocks occur is. So here there are four blocks they have given in order to measure a non-electrical quantity. So we have to know what is the correct sequence in which these blocks need to be placed. That is what we need to figure out. So out of the four options, option A is the correct solution of this question. So let's discuss something more about this one. So now there are four blocks which are the transducer, amplifier, instrumentation and the display. So now we have to know what is the correct sequence in these four blocks should be maintained. So therefore here, if you see carefully, there is a non-electrical quantity. So non-electrical quantity we need to measure. So always a transducer should be kept first, because transducer, the main function of transducer is to convert the non-electrical quantity to a electrical quantity. So out of these four blocks, only transducer can do this function. So therefore non-electrical quantity is converted into a electrical quantity. So whatever the electrical quantity we got, which might be a low amplitude signal, or we can say low power signal. So but we want a high power electrical signal. So because of that reason, only the amplifier is going to do that function. So therefore second thing, we have to keep a amplifier. So therefore amplifier is going to convert this low power electrical signal to a high power electrical signal or a high amplitude electrical signal. So now this has enough power or enough energy to drive an instrumentation. Instrumentation is nothing but it is a measuring device. Now I want to measure what is the accurate value of this electrical quantity. So therefore now I am going to keep an instrumentation block. Instrumentation block is, it's a measuring device. So therefore we are going to convert the electrical quantity into a mechanical quantity, because the pointer is going to move. So therefore it is a mechanical quantity. So therefore now the display, so now the display, so this mechanical pointer movement, it is now displayed by a display. So therefore I want to read what is its mechanical value. So therefore I am going to keep a display. So now I am going to get the accurate value of this one. So therefore now I am going to get a what is the accurate value of this measurement of mechanical movement. So what is the reading, so that we can get through the display. So finally by this all these devices we are going to place a transducer in order to convert the non-electrical quantity, and because of amplifier the low power electrical signal into a high power electrical signal. So because of instrumentation the pointer is going to get more, and then I want to know what is the reading. So I want to see it. So with the help of display I can know what is the pointer movement, then I can note down the reading for this non-electrical quantity. So with the help of this non-electrical quantity, so this much of electrical quantity it is going to give you this much amount of value. Now I am going to know the relation. So this is the correct way we need to keep the devices or the blocks. So now we are going to discuss the 14th question. See the question here. The core of a transformer is assembled with laminated sheets to reduce. So here the core of a transformer is made of basically silicon steel. So why we are going to use the laminations? What is the basic reason for using the laminated steels? So here out of the four options, option B, eddy current losses. So here we are using these laminations for the eddy current losses. So let's solve this numerical. In the previous question itself, I have already told you that here silicon steel is used for making the core of a transformer. So here iron loss in a silicon steel is equal to summation of the hysteresis losses plus eddy current losses. So because of silicon steel, basically the hysteresis loss is also going to get reduced, and also eddy current loss is also going to get reduced. But if you see carefully here, silicon steel laminations are used mainly to reduce the eddy current losses. So by default, by using the silicon steel, if you take a total core part without any laminations, still suppose if the hysteresis loss is equal to, let me assume 5 watt. So if you take a very core part, if you take a total core part of solid core of silicon steel, suppose if the hysteresis loss is equal to 5 watt, and if you think eddy current loss is equal to, let me assume 3 watt. Suppose if the silicon steel, if you made a laminations for this single core of solid core, if you make a laminations, then what is going to happen is hysteresis losses will remain same, because it is already decreased. So therefore, but eddy current loss will still further decrease, maybe up to 1 watt. So we can say that here with the help of silicon steel laminations, only eddy current loss is reduced. But if you take a silicon steel, if compared to any other materials, then hysteresis loss is still lesser than compared to any other materials. But with the help of laminations, only eddy current loss is reduced, but the hysteresis loss is constant with respect to single core and also with respect to laminations of a silicon steel. If you take a single core of silicon steel or solid core, or if you take a laminations of silicon steel, the hysteresis loss will remain constant, but only thing is eddy current loss is reduced. But if you take any other material other than silicon steel, the hysteresis losses may be, let me assume it is a 10 watt, but if you take a silicon steel, then its hysteresis loss is reduced. But if you take a laminations of silicon steel, hysteresis losses will be remain constant, but eddy current loss will reduce. So because of this reason only, silicon steel, I have already told you here, because of silicon we are going to add to iron, its resistivity will increase. As resistivity will increase, the current will decrease, so therefore the eddy current will decrease, so therefore the eddy current losses will decrease. So because of this reason only, eddy current losses will decrease if you use the laminations of the silicon steel. I hope you have understood the true meaning of solid core and lamination core. With the help of silicon steel, the hysteresis losses will remain constant no matter whether you use a single core of silicon steel or whether you use the laminations of silicon steel. But only thing is eddy current loss are going to reduce if you use the laminations of silicon steel. So now we are going to solve 15th question. See the question here. The EMF induced in the secondary winding of a 50 Hz single phase transformer having 1000 turns on its secondary is 222 volt. The maximum flux density in the core is 0.1 Weber per meter square. The cross sectional area of the core is. So basically this is a transformer. Based on this here, they also given the voltage which is going to induced in the secondary, which is 222 volt, and also they are given the number of turns and also the frequency also they are given, and also they are given the maximum flux density also they are given. So based on this data, we need to find what is the cross sectional area or area of the core of transformer we need to figure out. So what are the four options? Option B, which is 0.01 millimeter square, is the correct solution of this question. So let's solve this numerical. So basically here, the flux in the core is equal to sinusoidal, which is phi is equal to phi m sin omega t. So EMF induced in the winding of a transformer is N into number of turns into rate of change of flux. So if we do the differentiation of this one, we are going to get N phi m omega cos omega t. So this is a differentiation of this one. So here, this is the maximum value of the voltage. This is the maximum. This is the expression of the EMF. But I want to know what is the maximum value, which is Emax is equal to N phi m omega. But I want to know what is the RMS values of this induced voltage, which is, as it is a sinusoidal or cosinusoidal, so its RMS value will be maximum value by root 2. So therefore, N phi m omega by root 2. So omega is equal to 2 pi f. So 2 pi f into N phi m by root 2. So 2 pi by root 2, if you solve this one, we are going to get 4.44 N f phi m. So therefore, the basic relation, the induced voltage RMS is equal to 4.44 N f phi m. Phi m is called as the maximum flux in the core. See here, B is equal to, the flux density is equal to flux per area. But if I want to know what is the maximum flux density, because area is a constant, so therefore the maximum flux density will be maximum flux per area. So I want to know what is the maximum flux is equal to maximum flux density into area. So in place of phi m, I can substitute B into A. So therefore in place of phi m, I can substitute maximum flux density into area, which is the maximum flux density into area. So in the question they also given the frequency is equal to 50 Hz, and also the number of turns is equal to 1000 turns, and also they are given the EMF induced is 222 volts. See, the question they have not given whether it is a maximum voltage or the RMS voltage, but by default, if they are not going to mention anything whether it is a maximum or RMS, then by default it indicates it is a RMS voltage. So therefore, and the maximum flux density is equal to 0.1 Weber per meter square. So based on this data, we need to find what is the area of the core we need to figure out. So substitute all these values in this equation, which is EMF is equal to 222, this is 4.44, and N is 1000 turns, and frequency 50 Hz, and the maximum flux density is equal to 0.1 Weber per meter square. And now we need to find what is the area of the core. So if you solve this equation, only one equation with only one unknown, if you solve this one, we are going to get the area of the core is 0.01 meter square. It is a correct solution of this question. So now we are going to solve 16th question. See the question here. An additional condition for parallel operation of three-phase transformers over single-phase transformer is that. So here there are some conditions for in order to operate the parallel operation of transformer. So what is the extra conditions for operation of parallel transformer in three-phase when compared to single-phase transformer? So here out of the four options, option A is the correct solution of this question. The transformer should belong to the same vector group. So the transformer should belong to the same vector group. So let's discuss this one. So in this question they are asking what are the extra conditions for parallel operation of three-phase transformers when compared to single-phase transformers. So here if you see carefully, for parallel operation of three-phase transformers, suppose this is three-phase transformer and a three-phase transformer. So I want to connect a load here parallelly. So what are the conditions I need to take care? Suppose see here, this is a supply. So this is a supply, right? So I want to make a parallel operation. So there will be a dot polarity. So there will be dot polarity for the input and also dot polarity at the output. So always here we need to connect in a polarity fashion. So this input polarity should be connected together. So therefore these two dot polarities should be connected together and the remaining things has to be like this. Similarly here also same dotted polarity should be connected in a same, they have to be connected and the remaining things have to be connected here like this one. So this is the true meaning of this one. Then the remaining part we have to give it to the load. So this is the one of the important property. So the polarity should be connected together, whether in the source side or whether at the load side, they have to be connected here. That is the first condition. And also here if you see primary and secondary or source side and the load side, a three-phase transformer can be connected either in star fashion. Primary can be either in star or delta and secondary can also be in star or delta. So these are the different combinations of star star, star delta, delta star, delta delta. These are the different combinations we can make with the help of three-phase transformer or a single three-phase transformer. These are the different conditions, these are the different connections and also we can make here. So here see carefully, a star star, with the help of star star we can either make 0 degree or 180 degree. It is called as a phase to neutral or line to phase voltage with respect to the primary side or HV side and also with respect to the LV side. So 0 degree and 180 degree. And with respect to delta also we can make either 0 degree or 180 degree phase difference. And also with star delta we can make plus 30 or minus 30, plus 150 or minus 150. And similarly delta star we can make plus 30 or minus 30 degree, minus 150 degree and plus 150 degree. So total 12 combinations, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So total 12 combinations for a single three-phase transformer we can make. So here suppose if this three-phase transformer is a star-star connection, so then this three-phase transformer for parallel operation should be also same category, same star-star. Suppose here if it is 0 degree, here also it has to be same 0 degree. So therefore it has to be same vector group and also it has to be same phase sequence. Suppose if you are using here 180, then it is not going to connect, because here then we should not use these transformers for a parallel operation. So these three-phase transformers should be of same vector group, means star star means star star vector group, and also phase sequence. If it is a 0, yes, here also it is 0. Then only we can say, then only we can operate in a as for a parallel operation. So therefore they have to be same vector group and also same phase sequence. So therefore suppose if this is a star delta of plus 30 degree. So this transformer is of star delta of plus 30 degree. Here also this transformer should be also same category of star delta with plus 30 degree. It must not be any other degree. Like suppose minus 30 means you should not use, because this may have same vector group but the phase sequence is different. So therefore always you have to operate three-phase transformers with the same vector group and same phase sequence. Then only we can operate for parallel operation. So if one transformer is failed, the other transformer can use help in order to give the supply to the load. So therefore the supply will always remain no matter when other transformer is got fault. So these are some of the advantages of that parallel operation. So therefore here one thing you have to remember, they have to be same vector group and also they have to be same phase sequence for parallel operation, and also the polarity should be connected in the same fashion. They have to be connected to each other. Then only the short circuit current will not flow from one three-phase transformer to the other three-phase transformer. So this is the, and also here in a single phase transformer the voltage ratio should be also same for a single phase transformer. This is also same for the three phase transformer. But if you want to know what is the extra condition, they have to be same vector group and also same phase sequence. This is the extra point when compared to single phase transformer than the three phase transformer for the parallel operation. Now we are going to solve the 17th question. See the question here. The function of a brush and a commutator arrangement in a DC motor is 2. So what is the main function of a brush and a commutator in a DC motor? So what is the main function? So what are the four options? Option A, produce unidirectional torque. So this brush and commutator are used for to predict the uniform or unidirectional torque. So option A is the correct solution of this question. So let's solve this one. So now I am going to explain how a unidirectional torque is produced in a DC motor. So this is a DC motor, means we are going to give a DC supply to a motor. So here this is the armature conductor. So basically in a practical motor there will be a lot of turns in armature conductor, but I am going to take only one turn in the armature. So therefore here this is the north pole and this is south pole. So here this is a commutator segment. So it's a commutator segment, it's a conductor, basically it's a conductor, and this is a one turn which is armature connector. So basically this wire, this single turn made a soldering, means a soldering is made to this commutator A and the commutator B. So this end is made a soldering to commutator A and this end of the wire is made soldering to commutator B. So therefore this is called as a soldering. So therefore now these are called as the commutator segments. So between these commutator segments there will be some amount of insulator in order to make a gap between the electrical insulation between these two commutators. So here also there will be a small amount of insulator in order to not to make a short circuit. So here this is a brush, this is a brush 1 and this is a brush 2. So these are the carbon brushes. These are also connectors. So therefore now I am going to give a supply voltage VDC. So the current always goes from positive polarity. So current is going to flow here. So from the brush inside this commutator is going to flow like this. So current is going to make a closed path. So this is the way the current is going to flow in this motor. So if you see carefully here, the magnetic field always goes from north pole to south pole. So this is the magnetic field direction from north pole to south pole. So I want to know what is the torque or what is the force which is going to present on this wire, on this motor. So basically the force F direction is equal to I bar cross B bar. So the direction of the force will be cross product of the current and the magnetic field. So if you see carefully, the current in this manner, so the current is going inside. So like this one it is going inside and the magnetic field is in this direction. So if you take the cross product, so from current and magnetic field you have to take here. So current and magnetic field. So if you take the cross product, the thumb is going to downward. So therefore the force will be down direction. So on this connector, the force will be in the downward direction. So if you take the same principle to the other connector, which is the B connector, so if you see carefully here, the current is going outside. The current is going outside and the magnetic field is here in this way. So if you take the cross product, current and magnetic field, the thumb is going to show in the upward. So therefore the force will be upward. So therefore on this connector, on the connector B, the force will be upward. So therefore from one connector the force is downward and the other connector the force is upward. So therefore this motor is going to rotate in this fashion, anti-clockwise. So therefore this motor is going to rotate in this anti-clockwise direction. Suppose if it is made one cycle, means if it is made a one half loop, so therefore this connector B is going to come here and the connector A is going to go here. So half a cycle, half rotation, means 180-degree rotation. After that this connector is going to go to A and A is going to come to here. So the direction is also changed. See, as this wire is soldered to commutator, these commutators are also going to rotate. So therefore these are soldered. So if the wire is going to rotate, this, so because of soldering effect, this commutator are also going to rotate. So therefore B is going to come here and A is going to go here. But still the commutator brushes are constant or fixed. They are not going to change. So therefore this is the same one, brush 1 and brush 2. And same here also the current is in the same fashion, because current will always go from the positive polarity, and here also it is going to go inside, current here, and it is going to make a closed loop here also, same thing, it is going to come outside. So because of now apply the same thing, the magnetic field will be from north pole to south pole, here also north pole to south pole. And now I want to know what is the direction of the force on this connector B and connector A. So if you apply the same principle here the current is inside, and the magnetic field is here in this direction. So take the cross product of current and magnetic field, the thumb is in the downward direction. So therefore the force will be here. The force on this conductor is downward direction. And the same thing apply on the conductor A or wire A. So here the current is outward and the magnetic field is here. Take the cross product current and magnetic field, the thumb is upward, so therefore the force will be up. So therefore the force on this conductor will be up. So therefore on this conductor the force is downward, and this conductor the force is upward. So therefore again the motor is going to rotate another 180 degree rotation. So therefore at this condition, initial condition, it made a 180 degree cycle. And now it made another 180 degree cycle. So therefore it is going to come again to this position. So it is going to make a same way. So therefore always the torque is a unidirectional. So therefore the torque is going to make a unidirectional. So because of brush and commutator, what is going to produce? A unidirectional torque is going to produce. So this is the concept of this question. So now we are going to solve the 18th question. See the question here. The induced EMF in the armature of a lap wound 4-pole DC machine having 100 armature conductor rotating at 600 RPM and with 1 Weber flux per pole is. So basically they have given the lap wound winding and a 4-pole DC machine, and also given that the number of connectors in the armature which is 100, and also it is going to rotate with 600 RPM and with a flux per pole of 1 Weber. So based on this data we have to find what is the EMF which is going to induced in this machine we need to figure out. So out of the 4 options, option 1000 volt is the correct solution of this question. So let's solve this numerical. So in this question we have to find what is the EMF induced in a DC machine. This machine is the armature is going to connect in a lap winding. So lap winding is nothing but number of parallel paths is equal to number of poles. As the number of parallel paths are increased, so we can say this machine is used for the high current rating and also the low voltage. So therefore low voltage and the high current rating, and also the number of poles is equal to 4. So always the poles will be an even number, and also the number of armature connectors is 1000. So and also this machine is going to rotate at a speed of 600 RPM. So and flux per pole means each pole is going to produce a flux of 1 Weber. So based on this data we have to find what is the EMF which is going to induced in this DC machine. So the basic standard formula is equal to EMF induced is equal to total flux, means phi is the flux per 1 pole. So total flux which is produced in this machine is P phi. So P phi into N by 60 into Z by A. So based on this equation we are going to solve this numerical. So P is equal to number of poles is equal to 1 and the flux is 1 Weber, and the speed which is going to rotate. See this speed is in terms of the RPM, number of rotations per minute. So 600 by 60 into Z is the number of armature connector which is 1000, and here the number of parallel paths. The number of parallel paths is equal to number of poles, so which is equal to 4. So if you solve this one, finally we are going to get 1000 volt is the correct solution of this question. Small mistake I have told you here, the number of armature connectors are only 100. So therefore here I am going to keep here 100. So finally after solving this one we are going to get 1000 volt. So 1000 volt is the correct solution of this question. Now we are going to solve the 19th question of this lecture. See the question here. So stepper motors are used in. So basically the stepper motors are used in. So which of the following applications? So out of all these options, option A, printers. So in printers we are going to use the stepper motors. So now we will see in which different applications the stepper motors is used. So now we are going to discuss about the applications of the stepper motors. So before I discuss the applications of stepper motors, so what are the different types of stepper motors? So stepper motors are classified into 3 types, which are the permanent magnet stepper motor, synchronous stepper motor, and variable reluctance stepper motor. So these are the 3 different types of the stepper motors. So basically stepper motors are brushless. So now we can easily operate them because they are brushless, and also at what position the motor has to stop we can easily operate. So because of this reason the stepper motors are easy to operate. So here some of the important applications of the stepper motors are, they are going to use in recording heads in computer disk drives. So these computer disk drives are the rotating head is, so the rotating heads are also being easily operated with the help of stepper motors, and also the pins in the XY graphical patterns. Suppose if you take this earthquake, so during the earthquake suppose there is a pin like this one, the movement of this pin it is going to control by the stepper motor. So because of this we are going to know on the Richter scale how much amount of earthquake has been occurred. So it is also used in the XY plotter, graphical plotters, and also in the position of print heads. So on the position of the printers also we are going to accurately control with the help of the stepper motors, and also paper fed motors in typewriters and teleprinters. So it is also used in the typewriters and the teleprinters, where you have to constantly feed the paper into them. So the rate of motion of the paper in the typewriters and the printers are being controlled with the help of the stepper motors. And also it is used in the metering, mixing, cutting, blending and stirring. These are the different applications. And also it is used in the 3D printing equipment. Nowadays 3D printing is very much of high demand, so therefore in 3D printing equipment also we are going to use this stepper motors. And also in the textile machines, and also in the printing presses, gaming machines, medical imaging machinery, and also in the small robotics also we are going to use the stepper motors, and milling machines and welding equipments. So these are the different applications of stepper motors. Means in all these applications the stepper motor is used at a very high quantity, at a very large scale. So therefore these are the stepper motors which are used here. So basically in the printers also we are going to use the stepper motors. So because of this reason the stepper motors are used in printers. So now we are going to discuss the last question of this lecture, which is 20. See the question here. When inspection doors on the walls of boilers are opened, flame does not leap out because. So suppose if a person is came for inspection of the boilers, suppose if you open the door of the boiler, then what is going to happen? Whether the flame is going to come outside or whether the flame will be staying inside. This is what we need to discuss here. So out of the four options, the pressure inside is negative. So therefore the flame is not going to come outside of the window because the pressure inside the boiler is negative. So why like this we will discuss now here. So before I solve this question, let me tell a small example here. Suppose there are two papers. So paper 1 and paper 2. So here what I am going to do is, now I am going to blow air in between these papers. So I am going to blow air, very fast air between these papers. So what is going to happen now? So if you blow air between these papers, something phenomenal you are going to see, which is these two papers are going to come attract to each other. Means they are going to come to each other. Means the papers will be like this manner. So the distance between the papers will now decrease when you blow the air between the paper 1 and paper 2. Why like this? Because here when you are going to blow air between these papers, the velocity of the air between them is going to increase. As the velocity between the papers is increased, so therefore the pressure between the papers will decrease. So we can say pressure decrease means negative. So pressure decrease means negative. So here outward, so after these papers, means outside these papers the pressure is a very very high pressure, but here inside them the pressure is very less. So here inside them pressure is less. So less means negative, we can assume. High means we can take it as a positive. So outside pressure is very high. So outside pressure is very high, but inside pressure is very very low. So always there is a force from higher pressure to lower pressure. So because of this, because of high pressure outside, this paper is going to move closer to each other. So because of this phenomena, always because of high pressure, these papers are going to come close to each other. So same phenomena is going to happen here. Suppose this is a boiler in a power plant. So what is going to happen here? There is a lot of fire inside this boiler. Suppose one officer came for inspection and you want to see suppose you open the door of this boiler. So because inside this boiler there is a lot of amount of flame. So here by using some mechanisms they are going to make here pressure is equal to low pressure they are going to make here, because here the wind is very very high, and also because it's a very hot temperature. So here is a very hot temperature. So because of this the pressure will be very very low here. So but outside pressure will be very high. So because of this reason this fire will not come outside, because always it is going to go from high to low, but it never, because the current always goes from higher potential to lower potential. In the same manner here this fire will not go from low to high, it will always remain from in the low, because always the fire always goes from higher to low, but it will not goes from low to high. So because of this reason this flame will always stay inside, because we are going to say the pressure inside is low, or we can, in other terms we can say it is a negative pressure, and outside pressure is very high. means positive pressure. So because of positive pressure, this flame will not come outside, so it will always stay inside this boiler. So therefore this officer will not get affected with any burns or surgery. So by this lecture we have successfully completed the 20 questions, which are the questions of the TS Genco 2015 electrical solutions in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button, so whenever you upload a new video, the direct notification comes to mobile. If any improvements in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smiling, take care, and bye bye.